So, first of 3 chapters. Lesson 2, Architecture Part 1, we look at the physical structures, we look at the files. Lesson 3, we look at the processes. Lesson 4, we look at the memory structures. And how do we look at the files, the processes, the memory structures? We look at them by querying views. So, we know already, we'll go into greater detail the instance of the database. Remember the instance, memory structures and processes. The existence is transient, lives in your RAM and your CPU. The database existence is persistent, files on disk. What are those files? Here we see the 5 file types that make up an Oracle database. There are many other file types involved, but these are the 5 required file types. Every database will have a control file. Point of terminology, which I want to get out of the way on this very first slide. Point of terminology. Some people say that a database has 1 or more control files, plural. Other people will say that a database has 1 control file, singular, of which there may be multiple copies. The terminology I use is 1 control file, multiple copies. The Oracle documentation, in fact most documentation, is inconsistent. Sometimes they talk about the control file, sometimes they talk about the control files. But just so you know, I refer to 1 control file or multiple copies. All the documentation is inconsistent. A database will have 1 or more data files. 1 or more data files. A database will have 1 or more, well in fact it will have 2 or more, redo log files. Strictly speaking, temp files are optional. You can run a database without a temp file, but for practical purposes a database will always have a temp file, possibly several, and it will always have a parameter file. These are the 5 required file types, but there are several other file types kicking around which we're going to look at, which are indeed optional. But these are the 5 required file types. Now, we need some idea of how I/O works, some idea of some concepts and so on, and we need to know a bit of SQL. No problem with that. Well, I should say with regard to prerequisites, if ever I say something that assumes knowledge any of you don't have, if ever our manual assumes knowledge you don't have, for heaven's sake, say so straight away. It's best to deal with any questions at the time while it's fresh in our minds. Well, what I've just demonstrated is on the screen. Throw in questions immediately if possible. And you are allowed on Thursday to ask me about something we discuss on Tuesday. But ideally, it's best to deal with it in real time, as it were.
Well, then I'll ask one real quick.
Please.
What's the difference between the DBA tables and DBA objects? I mean, is one more inclusive than the other?
Oh, most definitely. If you look at DBA objects, you've got an extra column. Oops, DBA objects. We've got this column here, privileges, connect system / Oracle at, oops. Let me look at, there we go. Oh, I should have asked. If for any of you the fonts I'm using are not good enough for your eyes in the screen you're using, chat me a message or whatever, and I'll change the font immediately. So if we look at DBA objects, we see there's a column there called object type. Object type. So select distinct.
Can we play Batman?
Would you say that again? Font is very small. Thanks, Dave.
I'm sorry, I'm...
Let me make the font bigger there straight away. And raise to 12 by 16. That's better. Okay. Right. Select distinct object type from DBA objects. And we see that there are no less than 45 types of objects in my database, and only one of those object types is a table or a view. There's a view. And this is what, as you were saying, Scott, to DBA objects is a lot more inclusive, is a good way of putting it, a lot more inclusive.
Yeah, I use objects almost exclusively. I don't know why I should bother to use tables?
Depends what you're looking for. It's
Yes.
all a matter of what's in there. Because, and tables is one of the types of objects, it's because DBA objects is so limited in what it tells you. It will tell you that there is a table called Scott.emp, and that's about it. For real information, we're going to have to go to a lot more detail here where we get.
Okay, so if I want the detail, then I go to the tables.
Yeah. And that's why the little query I run here tells me the type of the object. And from then on, of course, I know what to go to next to get to fuller information. Now, so, database and the instance. So the instance then is your memory structures, your processes, the database files on disk. And through the instance, remember how I sketched out the session architecture, the instance mediates all access to the database. So a session, not shown on the slide, it was on my first diagram at the beginning of our session this morning, the session then never touches the database directly. Sessions always work through the instance. The database is completely protected by several layers from users. No user has any direct connection to the database. This is the rack environment, multiple instances hitting one database, but that's more than a little bit out of scope for the purposes of this week. This picture we're going to see in all of these 3 chapters. It's a creditable attempt to describe a complete Oracle server in just one slide. So, what do we have? Well, taking it from the physical structures, we have data files, we have control files, we have log files in various forms. We're not showing here the parameter file or temporary files, don't worry about them. Then there are a number of processes. So this chapter we'll be looking at the file structures, the control file, the data files, the log files. In the next chapter we'll move on to process structures, processes PMON, SMON, MMON. We'll look at what the processes are, and in the third chapter on architecture, we'll be looking in reasonable detail at the memory structures. Here we see sessions coming in, server processes talking to user processes. Remember, user processes talk to server processes talk to the instance, and the instance via background processes write to disk. So to give an example of what happens if I connect, and right now I'm logged on as a user system. So remember my original diagram here. You, Paul, won't have seen me build it up, but we have users talking in communication with the user process in communication with the server process communicates with instance communicates with the database. So if I connect as Scott Tiger at the connect string there, in the later chapter we'll break down what's actually happening. Right now, there's me, you can't see, in communication with the user process. What's the user process? SQL plus this program in right now. So the user process is running on the client side. So me and my user process are client side. On the server side, server process, instance, and database. And we can see what those things are. If I didn't actually ask if you were all familiar with Unix. I'm going to assume you are for the time being, and if any of you aren't, we'll plug that gap in later, where necessary. But if we look at what's happening on the server, what are the processes running on this server? We have this simple command. If any of you are not familiar with Unix, all I'm doing is identifying, listing all the processes to include the string class. And here are what we call the background processes. There's one called PMON, PSP, VKTM. These are what to call the background processes that make up an Oracle instance. Background, they're running all the time. Then we have what are called, some people call them foreground processes, I call them server processes. Whatever terminology you please, foreground process or server process, I use the term server process. These are the server processes that are making up sessions. One of these sessions, local equals no, means it's coming through a network. This one, local equals yes, is someone connected directly without coming in through the network. But these things are the server processes. And the session, in my case, will be SQL Plus running here on Windows, and one of these guys will be my server process. I could work out which, we can reverse engineer that, but not for considerably later in the chapters. But one of these will be the server process to which I am connected. The server process then communicates with the instance communicates with the database. The instance is a big block of shared memory. I suppose I could have added to my diagram here the technique by which the communication occurs. The communication is via background processes that make up the communication between instance and database. And the background processes are these guys here. So that's the rather more intelligent way of sketching out what we're looking at. In this chapter, we'll be looking at the files. I wanted to introduce at this point Oracle's storage model in terms of an entity relationship diagram. Now, I'm a database administrator. All database administrators are infatuated with normalization. I normalize everything. And you need to memorize the left and center parts of this diagram. The right-hand part I've included for completeness, but I'll deal with that in the space of about 30 seconds. The Oracle storage model. We have logical storage and physical storage. Now, you were all at college much more recently than me, but I do remember this. And many, many years ago, back in 1970, late 60s, early 70s, when Ted Cord invented the relational database, Ted Cord said that logical storage and physical storage must be completely separate. So what are they? Well, the logical storage is what the users see. The users in this context being the programmers, the developers. The physical storage is what the system administrators see. So, what do physical system administrators see? They see data files, and data files are formatted into operating system blocks. So you might have a data file that's a gigabyte big, and your operating system will store that data file as a series of OS blocks, perhaps 1K blocks, whatever size they may be. And that's what the system administrators see. What the users, the programmers, see is tables. And when I issue a command such as select star from dept, what am I addressing? I'm addressing a table called dept, and those are the rows within it. And I have no way whatsoever of working out physically where that thing actually is. I have no way of telling where those physical rows are, because all I'm seeing is a logical structure stored within a segment. Definition of a segment we'll see shortly. So the programmers see only the logical structures down the left, and they can't ever work out what's happening physically. Equally, the system administrators, they see a data file. They see this 20 gigabyte data file, and the system administrators have no way of telling what logical structures are stored within it. And that's the rules of a relational database. And the rules are there because Ted Cord said we must have an abstraction of physical storage from logical storage. Why did he say that? If the programmer knew where... Oh, I see the question from you, Kathy. Is this diagram in the book? Let me just check whether it made it to the final release of the book, because this is a recent and... No, it isn't. Right. Not in the version of the book I've got here. I'll check that out and check the version control as to whether this diagram is in there. Thank you for asking, by the way. So we should have, I'll mail this through to you in any case, just in case. We need complete separation. Why? Because if the programmer knew where those blocks were, if the programmer knew physically where these rows were, anything done at the system level, renaming a data file, moving a data file, resizing a data file, will break the application. It will break the application. But because we have the abstraction, I can do what I like with the physical file, and as long as I don't actually delete it, I can rename it, I can reorganize it, I can move it around, I can move it onto a different disk structure, whatever it is. And the software I write, i.e. that very simple program here, will still function. Right. So we have abstraction of physical storage from logical, and that's a requirement of a database, requirement of a relational database. How does Oracle do it? Well, physical storage, data files are formatted as Oracle blocks. Oracle takes it to different levels. The segment, your typical segment is a table, but segments come in various types. So, what are the types of segments? Well, if we look at, guess what? DBA segments. and you know how to find out which doesn't exist because I'm logged in as someone who can't see it. So let me connect as system/Oracle at compute one connect as a user with some privileges. I think I copied that. Got that completely wrong. And class, right. Connecting as user system. And now we'll look at DBA segments. And we see that every segment has a name, and every segment is of a certain type. Right. So if I were to select segment name, segment type from DBA segments, I'll put in a predicate where owner equals Scott. There we see that Scott in fact has a total of 5 segments. What are those segments? 2 of them are indexes, 3 of them are tables. So a segment then is a structure that contains data, and there are various types of data. In this case, the data may be index data or maybe table type data. There are about a dozen different segment types. Run your own query, see how many segment types there are and how many of each segment type. So a segment, typical segment is a table. Then segments are stored in table spaces, and this is our abstraction. The table space, one database administrator, the person who first taught me database administration, he used to describe a table space as being your toy box. And I never had a toy box as a kid. Apparently people used to have, some children have toy boxes. And a toy box, so I'm told, is a big box into which you throw your toys. Don't know if any of you were messy like that. I never had one. So you throw your toys into the toy box, and you let the toy box handle the storage. And the analogy is, when you create a segment, such as an index called pkemp, or a table called emp, you nominate the table space in which the segment will live, because each segment lives in exactly one table space. So note, many to one. One table space can store many segments. One segment exists in exactly one table space. And physical storage is handled by the data file, by the table space interacting with the data file. So all the programmer does is create the segment, nominate a table space. The table space, like the toy box, you throw your segments into the toy box handles the storage. A table space will consist of one or more data files. And because there's only an indirect connection, you have no control over which data file a segment ends up in. Furthermore, note many to one, one to many. Navigate through that relational structure, and you'll then see that one segment might in fact be distributed across multiple data files. One data file may contain bits of many segments, because you have many, cut out the table space. And what have you got? You've got many to many. So in relational engineering terms, there's a many-to-many relationship between segments and data files. One segment can exist with one segment to be splattered across many data files. One data file can contain many segments. But of course we don't permit many-to-many relationships because we're all good relational engineers, and the table space resolves that problem. Navigating further down, a segment, skip out extents for the moment, a segment consists of many Oracle blocks. An Oracle block is, by default, Oracle blocks are 8 kilobytes with the current release. So one segment will consist of many Oracle blocks. It will be ludicrous to allocate space one block at a time. Now, if your segment is going to be a gigabyte big, you wouldn't want to be managing space 8K at a time. So we group blocks into what are called extents. An extent is a set of consecutive blocks. So your block size might be 8K, your extent size might be a gigabyte. So an extent, in that case, will consist of 128,000 blocks, which you could manage as a unit. But an extent is nothing fancy, it's just a set of consecutive blocks. So a segment consists of many extents, which are many blocks. And at the bottom of the diagram, One Oracle block is usually multiple operating system blocks, usually. In a typical Linux environment, your Oracle block size might be 8K, your operating system block size might be 1K. So we close the diagram, we resolve the diagram in that direction as well. We resolve the many-to-many relationship two ways, via the tablespace entity and via the relationship of block to block. Right, so hang on to that throughout the next week, the Oracle storage model. Physical storage with system administrators C, logical storage, which the programmers see, and only we as DBA can relate the two together. Over there on the right, just for completeness, ASM is automatic storage management. It's Oracle's alternative to file system storage. It has wonderful capabilities, wonderful benefits in some ways. Whether it's suitable for all databases is open to debate, but it's certainly suitable for many databases. Oracle takes control of the physical storage as well as the logical storage. That's what ASM is. The data file becomes an ASM file, and an ASM has its own storage structures within it. So it's Oracle replacing the physical storage section with its own storage model. So memorize this diagram, and if it really isn't in the manuals we sent you, we'll make sure you have a copy of it. Okay, so what are database files? So going back a couple of slides, remember your basic file types. We've got control file, database file, reader log files, temp files, parameter files. We now dive into the data files, which, previous slide, are where we store all our data. Now, user and system data is of course the data dictionary. Tables and indexes, they contain the segments. Why? Because they make up the table spaces. So the logical table space gives you the abstraction of physical storage from logical. Table spaces then have to be created, and there's your most basic syntax. There's any number of extras you can put on this syntax. I'm going to start working under Unix. I'm annoyed with having to reconnect all the time. Let me just change the font. Just raise that font to 12. Apply. Right. SQL plus /assistdba. This connect syntax will be broken down in later chapters, but right now I'm logged on as user sys, which means I have total power. Most basic syntax for creating a table space. Create table space. Table space. Slight performance issues. My TS. Data file. Nominate a data file. Data file. My TS1.dbf. I'm not giving it a full path, don't worry about that for now. Give it a size. Size 1 megabyte. That will have done two things. It's created the logical structure, the table space, and the physical structure, my TS. So, to see what I've done, what do we do? Well, we should know by now. If I, for instance, how do I find out about my table spaces? Run my little script. Table space. And these are then the views that will give me an idea of what's happening with table spaces. And there is a view called DBA table spaces. Remember, DBA, that's a fixed, or not fixed, sorry, that's a static view populated from the data dictionary. Then there is another view called the underscore dollar table. Who am I logged? Oh, I'm logged into this. The underscore dollar table space. Oh, I've done some. There we are. $, that's the one I want. $, table space. That's actually a synonym. This is why I go to all objects to get the full picture. You can see what's going on here. There's a view called DBA table spaces. There's also a public synonym called DBA table spaces. There's a view, the underscore dollar table space. And if you were to look at the source code, which we can see later on, there's a public synonym called $, table space. And normally one would go through the synonyms being DBA table spaces, $, table space. So looking at these two, we'll see they're very different information. $, table space. My performance is degrading. $, table space. The table space has a number, the table space has a name. and a few other bits and bobs. So select star from. $v table space. Correct my spelling. Oh gosh. Select star from $v table space. And there's my new table space just been created. You cannot choose the table space number, you wouldn't want to. Now, but there's not much information there. You know, we've got 4 other files, 4 other columns I should say, and that's about it. Whereas if we look at DBA table spaces, rule of thumb, most $v views are singular, most DBA views are plural. But I only say most. We get a lot more information. Note the block size. I did mention that, default 8K. You get that status that we saw in the last chapter, online, offline, read-only. The type of information that's going to be within it. Not, you know, the type of, it's not the contents, it's the type of contents. There's a lot more information in the view that's populated from the data dictionary. And that will come to where these views are populated from as a vital point. DBA table spaces is populated from the data dictionary, it's a data dictionary view. $v table space is populated from a control file, which we'll see shortly. Now, to complete what I did when we created the table space, we know from my diagram back here that a table space consists of multiple data files. Okay, describe $v data file. And $v data file, every file has a file number, every file has a, what's the word name? Every file has a name. And every file is part of a table space. And that's your join column. So TS hash is the join column back to $v table space. So to get a physical structure, the physical layout of my database, I can select $v data file dot name, comma v. Let's give it join $v. Don't be stupid. $v data file name, $v table space dot name from, and any syntax I like here, but $v data file join $v table space using TS hash. And there we see the physical structure of my database. There's a table space called system, there's its data file. One called sysorgs, there's its data file, and so on. Note the many-to-one relationship. At the moment, I have only one data file per table space. Simple syntax. Alter table space my TS, add data file. Give it a second data file. Add data file, my ts2.dbf, size 1 megabyte. I wouldn't say what I'm doing of letting Oracle choose for this sort of thing is necessarily good practice. I'm not creating these things in a very sensible location, but don't worry about that for now. And there we see that there are now 2 data files making up the one table space. So that's your basic syntax. Then we create the table within a table space. So create table, well, I'll put it in the Scott schema, scott.t1, c1 date, nominate a table space, my TS. And that's, going back to the diagram here, I've said the table is a type of segment, and I've told Oracle which table space to put the segment in. And that segment will have some sort of physical existence. It will be at least one block, well, at least one extent, and the extent is at least one block. But physically, I have no idea which of those 2 data files it's in. Furthermore, as a programmer, I cannot find out. I can find out as DBA. And that's where, well, what's a segment? A segment is the container which contains an object. So the segment is the table, in that particular case, divided up into one or more extents, and each extent, one or more blocks. Now, there's DBA data files, 1 row for every data file, fine. DBA segments, one row for every segment. Now there is an 11G anomaly here. There's not an anomaly, it's an 11G feature. But it can confuse the heck out of you if you aren't expecting it. Remember what I said earlier? Going back to my diagram, you see I keep going back to this diagram. The segment, your typical segment is a table. But there's actually a rather odd effect at this point. If I look at, select table name from DBA tables, select table name from DBA tables, where owner equals Scott. Select table name from DBA tables, oh, I've got a spelling mistake there, where owner equals Scott. We see 5 tables. If I then select segments name from DBA segments, where owner equals Scott and segment type equals table. Right, I want one of you to look foolish when you take a guess at how many rows do you think I'm likely to get back when I run this query. Who's prepared to have a go?
I'm prepared to have a go, but I haven't got a clue. Let me think about it for a second. Wait a second.
Mm-hmm.
I had my.
I don't know how many segments we're talking about.
Right. Select table name for DBA tables where owner equals Scott.
Oh, I know the
Scott
answer.
owns 5
Okay.
tables. Do you? I hope you're going to get it wrong. Right. Remember?
I'll guess. I'll say 15.
You're not trying, man. What are you going to get back? 3. This is an 11G anomaly. Remember what I said? A segment, every table exists as a segment, but there's an 11G feature. You would not get this effect in any release earlier than 11G release 2. From 11G release 2, well, I'll show you what's going on. If I insert into T1 values, how did I create T1? It was a date column. I'll do an insert values sysdate. Scott.T1. Change T1 for Scott.T1. So 11G release 2 only. I've now inserted a row. I'll rerun that query. And what we see is like magic, the segment has been created. This is 11G release 2. Right.
But John, back up on the whole concept. So I was going to get the answer wrong because I was going to say that there was going to be 1 segment per table. And you had
That's what I was hoping someone would say.
You had 5 tables, so there must be 5 segments, right? And that's the way it sort of should be. But
That's the way it was up to and including 11.1.
Okay, so let's review this. A segment is a structure that holds a table or a index. As long as we're not talking about partitioning, right? Take partitioning out of the mix. And John, you stop me if I'm incorrect, because I'm sort of think I'm right. But a segment holds an object, a table or an index. And the answer should have been 5, but there's a screwiness in 11G release 2. Fair enough?
That's exactly it.
Okay.
From 11G release 2, by default, the segment does not get created until data is inserted into the table. So I know by deduction there can be no rows in bonus. Select count star from Scott.bonus. This has to be returning 0, especially if you spell from correctly. Change, oh dear, 00940. There have to be 0 rows. So from 11G release 2 onwards, the segment is only created when the table actually has data within it. That can cause a lot of confusion. It confused the heck out of people when the 11.2 upgrade came out, because it was documented, but I'm one of the few people who actually reads the documentation for each new release, and that was the problem. So just bear in mind, it's not an anomaly, it's just the way 11G Release 2 works. The segment is created only when the table has a row inserted. So coming back to here, the segment is the container for the object. What's the object in my case? The table. And the segment, but from 11G Release 2, the segment is in fact only created when you need it, in effect. Now, DBA data files, we've seen that. Every data file is part of a table space, and normally you would do the join to get more information about the table space. Now the join column, we've already seen the query I ran against the $$ views. The join column for the $$ views is TS hash. So to join $$ data file to $$ table space, there's the join column. If you're working from the data dictionary views, DBA table spaces, you get the table space name, not the table space number. If you look at DBA data files, you get the file name. You do get the file ID, but file name. So your join column here, if you were going to join DBA table spaces to DBA data files, what's your join column? It's table space name. And you'll work out whether you prefer to query DBA views or $$ views, because there is a big overlap. But they do contain different information, and there are certain occasions when you will want to query one rather than the other. DBA segments, one row for every segment. And as just demonstrated, the segment may not be created. Just for completeness, if you look at DBA tables, see that column there, segment created? That's what we have from 11G Release 2. 11G Release 2 tracks whether the segment actually exists. There is no column for the name of the segment. The name of the segment is always the same as the name of the table. Now, has the segment been created? Is the interesting one. So if I were to select table name, segment created from DBA segments where owner equals Scott, now we see DBA tables, not DBA segments, my apologies, DBA tables where owner equals Scott. And there we see the bonus table. The way I think of it, the terminology I use, the bonus table exists, but it's purely a data dictionary structure. It has no physical existence. It hasn't been instantiated because the segment hasn't been created yet. Why not? Because no one's put a row in it. And it makes sense. You know, what's the point in creating a physical structure if nobody's put anything into it? Now, so that was data files. Data files are your repository for data, but the storage of the segments is abstracted by the table space entity in between. Our next physical structure is the log file. Now, log files come in several forms. The terminology read your log file, if you're being finicky, you wouldn't use the term read your log file, you would call them online read your log files to make the distinction. But when someone says read your log file, they always mean online read your log file. But strictly speaking, you should always specify online read your log file, or archive read your log file, or standby read your log file. But I think it's fair to say that when someone says read your log files, everybody assumes they mean online read your log file. But never forget, read your log files do come in different types. So, rules of a relational database. Ted Codd said that any relational database is not allowed to lose data. You know, if your database can lose data, then it's not a relational database. That's the rules. Now, the way Oracle and I think all third-party products implement that rule of a relational database is by logging changes. So what Oracle does, whenever you change data, we write the changes. Eventually, the changed data will go to the data files, but only indirectly. only very indirectly, because remember what's happening back here. If your user inserts a row, his user process will send the row to the server process. So when I did that, my user process constructed the insert statement. How? By prompting me to type it in. Of course, in a more sophisticated environment, it would be a form you would fill in, then you would click the submit button. But one way or another, the user process constructs the insert statement for the row. That insert statement with the row data is then sent to the server process. How? Usually across the network. The server process then inserts the row into the instance. So at that point, the row exists only as a memory structure. And eventually, it will get written to the database, where it becomes persistent. But the write to the data files, the write, in this case, to the segment that consists of that stores scott.t1, the write to the data files is asynchronous. It is not written in real time. There's nothing to do with whether I commit the transaction or not. If I insert another row and commit, has that data been written to the data file? I have no idea, but almost certainly not. Oracle does not write to data files in real time. If it did, the performance would be disastrous. But Oracle is not allowed to lose data. So what does it do? It writes out sideways the change vector. The change vector. And where does that change vector get written out to? The online redo log files. Now, the change vector is usually very small. Come back to the diagram here. The Oracle block. The Oracle block is the unit of I/O. So if you want to read one row from one table, you will read the block containing that row. Well, my rows are tiny. My rows are tiny. Now if I select star from scott.t1, those rows are tiny. But to read that row, what Oracle actually did was present me with an entire Oracle block, 8 kilobytes. Now, when we insert the row, we don't have to write out an 8 kilobyte block. We need to write out the minimum change vector that will be needed to redo the work. Now, this is important for performance reasons. The redo logs contain the minimal change vector required to redo the work. So you update a block that's 8 kilobytes, but your actual change vector might be 50 bytes. It's only that change vector that goes to the online log file on disk. There's a lot more than that on this slide. So we will return and complete this. This will make a bit more sense in a couple of chapters' time. But this is what happens when you do DML. Your user process generates the statement, which might be insert, update, or delete. The server process then executes the statement in memory. In memory. Which bit of memory? The buffer cache. The buffer cache is a part of the instance that we'll see in 2 chapters' time. So the insert, update, delete occurs in memory. The change vector is also written out sideways to another memory structure called the log buffer. So when I did this insert here, what happened, among other things, is that the block containing the row, or because it was an insert, the block that will contain the row, was copied from data file into memory. It was copied from data file into memory. Then the insert occurred in memory, and the change vector was written to the log buffer. The block in the buffer cache is not written back to the data files in anything like real time. It might stay in memory for seconds, minutes, hours without being written to disk to the data files. Because when it is written to the data files, there will be an 8 kilobyte block that goes. Whereas my insert might have been just 50 bytes of read, 50 bytes of data written to the log buffer. The log buffer is written to the redo log files in near as damn it real time. Near as damn it real time. And when I say commit, it is real time. This is vital for understanding of the Oracle architecture. I hope one of you is going to ask a question at this point, because that will show you don't understand, and then I get the excuse to go through it all again. What do you have to hang on to? We copy data into memory to the buffer cache, and that's where we execute all the code. So the buffer cache is a memory structure of the instance containing blocks of data where we insert rows, delete rows, update rows. The change vectors go to the log buffer. That's another structure within the instance. It's another memory structure, but it's a very small structure. And the log buffer is flushed to disk. Where on disk? The read log files. Now that is flushed in near as damn it real time. And when you say commit, it is real time. This, by the way, is vital for performance. It's also Oracle's definition of a committed transaction. Ted Cord said committed transactions can never be lost. So what Oracle implements that by saying we do the work in memory, and then when we issue a commit, we flush the log buffer to disk. We flush the buffer to disk.
John?
Yeah.
You're showing that the redo logs are writing to, I guess it's an archive process, the green circle?
That's eventually. Haven't got onto that yet.
Okay. All right, so we're not yet at the point where it's actually writing to the data file.
No, we aren't. No, we aren't. The sequence of events. The work is done in memory, and in very nearly real time, the change vectors go to the log files on disk. Nearly real time. There's a process called the log writer, and the log writer is monitoring this log buffer, and in nearly real time, log writer flushes it to disk. When you say commit, your session hangs, while log writer really does write the log buffer to disk. But it goes to disk in nearly real time anyway, and that means that the commit is going to be virtually instantaneous. If I insert another row, like that, I've inserted another row, within a fraction of a second, the change vectors will already have gone to the log file on disk. Yeah, it's nearly real time. And then if I commit that insert, there's probably nothing to do because the change vectors are already on disk. But the blocks themselves will almost certainly still be in memory. And the blocks containing the rows have almost certainly not been written to the data files. The write to the data files is asynchronous. So hang on to this then. The write of change vectors via log buffer to disk is nearly real time, and it's a synchronous write when I do that. The write of the change blocks with the actual complete rows to the data files is asynchronous, and it might occur after a significant time delay, which could indeed be minutes, could indeed be hours. Why? Because Oracle says disk I/O is bad for performance. And just because you've committed a transaction is no reason to write it to the data files. Someone might be rereading the data. I might query the data back immediately. So what's the point in writing it to disk? I want to keep it in memory. And this is one of these parts where Oracle differs from some competing products. Do any of you work with SQL Server? Any of you SQL Server people? Well, if you are, you're not admitting it, right? I'm not sure if it's still true, but to the best of my knowledge, in a SQL Server environment, when you issue a commit, the actual blocks get written to the data files. Oracle doesn't do that, and why should it? All you need to do is write the change vectors, because in memory, you've got the real-time information. So the fact that the data files are out of date doesn't matter. Real-time information in memory, and enough change vectors written out sideways, you could regenerate the work if anything went wrong. Right, so redo then protects all committed transactions. Okay, this is a vital bit of architecture, and I'll be testing you on it later on. So, if that's cool with you, more detail. So the theory, previous slide, was this.
I'd like to interrupt one thing. So I'd like to ask the students a question based on the last slide. Previous slide there. And maybe you said this, but if you did, good. What happens if the instance crashes before the buffer cache is flushed to the data file? Before the row inserted or updated is written back to the data file? Paul's so
This
lucky.
is a vital test of your understanding.
Paul's so lucky he can't talk to us today. He's not on the hook here.
Well, my understanding is that if it doesn't get written to the data file, it's not updated. It's residing in an archive log somewhere. Maybe. Okay,
so that's fair enough. So and let me even be more precise. So the change has been committed, which John said it makes it go to the redo log, more precisely the online redo log. But then the instance crash occurred. Somebody pulled the plug on the server and the backup unit failed. So it's in the redo log, but it's not in the data file. What happens when the database comes up?
Doesn't it check the redo logs for the transactions that are waiting to be moved over to the data files?
Yeah, I'll take that as a winner. I'll take that as a winner.
Using an SCN?
Absolutely. And Kathy's chatted us in here. When this comes back up, it has to sync up with the redo logs. Yeah, excellent. Nice work. Back to you, John.
That is exactly it. This, by the way, is why it's impossible to corrupt an Oracle database. We'll return to this later on when we go into greater detail on how DML is done, because what we haven't covered is what happens with uncommitted transactions that did get written to the data files. Because remember, there are two issues here. There might be a committed transaction that did not get written to the data files. It's also possible for an uncommitted transaction to be written to the data files. We haven't covered that yet. So, as you're saying, Paul, the redo log is a physical file. It is a physical file, and we come to our favorite query. We have views that show you where they are. First view, $log. I said, you're right. No, you're right, Paul. You're right, Paul. The log, as such, is not a physical structure. The log file is the physical structure. So we do have some abstraction going on here. Yes, the redo, yeah, the terminology is a bit loose, and I'll tighten it up right now. We have what are called log file groups and log file members. $log, right. This is always a bit difficult to sketch out without a whiteboard. The redo log consists of 2 or more groups, and each group consists of 1 or more members. So 2 or more groups. Why there are 2 or more groups will become clear in a moment, but 2 or more groups, and each group consists of 1 or more members. And there's the join column that takes you back. So if I were to select group hash and members from $log, we find the redo log for this database consists of 3 groups, and each group has 2 members. Right, what are the members? Well, select group hash, and I'll choose type and member from $log file. And here we see the physical structures. Note, type is online. There are, strictly speaking, there are 3 types of log file: online log files, standby log files, and archive log files. But for practical purposes, type is always online. So we have a total here of 6 members. So group 3 consists of these 2 physical structures. Group 2 is these 2 physical structures. So the log is a logical structure consisting of these physical structures. And what this slide previously is showing is this is really the logical structure consisting of 2 or more groups, each group being 1 or more members. Right. Now, the log file groups are used in a cyclical fashion. So we'll go back to groups, and what I shall do is select star from $log. Okay. So group 1, thread is only to do with rack. Forget that for now. In a racks database, you will have multiple threads. So to sketch out what's actually going in terms of an entity relationship diagram. As ever, when in doubt, normalize it. The way the structure works is we'll have the database at the first level, and the database will contain, or include I should say, at least 2 online log file groups. Redo log group. At least 2. And each group will consist of at least 1 member. It should be more than 1. When you become fully competent DBAs, you'll be normalizing everything like this as well. The database contains multiple groups. The group consists of multiple members, and the members are the physical structure that make up the redo log. Now, logs used in a cyclical fashion. Oracle streams out the change vectors in near as damn it real time to one group. Which group? The group whose status is current. So let me select group hash and status. I'll also take sequence hash for reasons that will become clear later on from $log. So right now, group 3 is the current group. So at this precise moment, when I did that insert and commit, the change vectors were written out to the physical members that make up group 3. However, a log file group, the members are a fixed size, and you see the size here. If we look at bytes, group 3 is 50 megabytes, 50 megabyte members. So each of these files is 50 megabytes big. Proof of it, ls minus lh, and so looking at just one of these things, that physical member is indeed 51 megabytes. Nice. So that's rounding, of course, because megabytes going to. Yeah. So group 3 then is members that are 50 megabytes each. There are, as we see here, there are 2 members each. Oracle keeps both members identical. Because the change vectors are critical for recovery after a restore, they can, you should always have at least 2. Oracle requires 1 member per group. Any decent DBA will have at least 2 members per group. And Oracle will always write the change vectors to both these members as a parallel write. Parallel write. So that if one gets damaged, we still got the other. Now, because they're fixed size, eventually they're going to fill. So when we generated 50 megabytes of redo, the members that make up group 3 will be full. At that point, we have a log switch. We have a log switch. What that means is that we cease writing redo to group 3 and start writing redo to the members that make up either group 1 or group 2. And that's where the sequence number comes in. I could do a load of DML. If I create table big as select star from all objects, that'll be a reasonable size table. What's happening with the redo? I'm still streaming out data to there. I'll do a bit more work. Insert into tbig, select star from tbig. And that will be another 70-odd thousand rows going in. I'm generating, oh, there we go. I'm generating quite a lot of redo. And the change vectors are being streamed out to group 3. Still going to group 3. Insert another 140,000 rows. Let's insert another 280,000 rows. And by now, I should have filled the members that make up group 3. What's happened? I've generated over 50 megabytes of redo with my big transaction. Therefore, we filled group 3, and we had what's called a log switch. Oracle stopped writing the redo to group 3 because it was full, and has started writing the redo to group 1. After another 50 megabytes of redo is generated, we'll have another log switch, and then we'll start writing the data out to group 2. When we generate another 50 megabytes of redo, another log switch, we will overwrite the files that make up group 3. So we loop through the redo log file groups in order, not in order of group number, by the way. It's in order of which it hasn't been used for the longest time, and that's where we come to this column here. What this column here is telling me is that since this database was created, there have been 37 log switches. You could even do the arithmetic. That means I've generated 37 times 50 megabytes of redo since the database was created. And we always overwrite the oldest log file group, which happens to be going through them in group number order. Yeah, but that is only a coincidence. So, fill a log file group, log switch. At that point, I'm going to talk about checkpoints later on. So we'll skip the term checkpoint for now. Very briefly, a checkpoint is a forced write from memory to data files. A forced write from memory to data files, which Oracle tries to avoid doing. Oracle tries to avoid writing to data files at all possible costs, because it's bad for performance. But there are times when it has to, and that's known as a checkpoint. So you require at least, let's be precise in our terminology, you require at least 2 online log file groups. Why? Because if you didn't have 2 groups, it would be impossible to switch between them. And the idea, of course, is that once you've switched out of one group into another, you back up the group you were using previously, which is what we see on the previous slide. When you fill a log file group, another process kicks off and copies it out as what we call an archive log file. So the redo then is generated in real time in the buffer in memory, written in very nearly real time to the online log files. When an online log file group fills, the archive process, which we'll see later on, kicks off and copies it out to a separate log file group, log file type called an archive log. And that will be your long-term history of every change vector ever applied to the database. Okay. So you loop through your online log file groups. And that we should see, well, down there. Archive log mode, that's what I briefly brushed into. That will be the copy. So going back 2 slides. Archive log mode means copy the log file groups as they're filled. If you do not run your database in archive log mode, you are vulnerable to loss of data because you wouldn't have that history of all changes. Right. Okay. And we'll cover archive log mode, by the way, in a much later chapter. We've got a whole lesson on managing redo log. So, next data structure, major disk structure, the control file. So terminology, I talk about one control file. Choose whichever terminology you're happy with. The control file tracks the physical structure of the database. You can attempt to reverse engineer it, but how do you find out about it? You query a view. Select star from the $control file. And we find that my database has 2 control files, what I prefer to call it, 2 copies of the control file. That's one copy, U01 app, Oracle, or a data class, whatever. Then there's another copy in a totally different directory. And any decent organization will have a standards handbook that says all production databases will have 3 copies of the control file on 3 different devices or whatever. The control file is small but vital. So if you look at it, right, I'm looking at that thing. We find that our control file is less than 10 megabytes big. If we look at the other one, we'll see that that should be identical. And indeed, it's exactly the same size. The timestamp, at least to the accuracy of the minute, is the same. The 2 control file copies are synchronized and kept identical. Any writes to the control file are parallel writes to both copies. Parallel write to both copies. Because they must be kept identical, because if they're out of sync, Oracle will be totally confused. What's in these things? Well, as the slide says, among other things, the control file tracks the physical structure of the database. And you can get some sort of idea of it. I mean, you're never meant to look at the control file with any sort of operating system utility, but there's no, we can get some sort of information out of it. I'll just use strings, strip out the binary characters, and send it through more. And here you go. Within the control file, we've got the name of the database, presumably, upper and lowercase versions. Here you see the online logs are indeed listed. Here you see my data files. Those are the two data files I created. There we even see the table spaces. And this is where you can begin to understand where some of the views we were looking at earlier came from. The view $v data file is populated from the control file. It's this. The view $v log file are populated from the information here. $v table space is populated from that. So to return to here, the control file, among other things, tracks the physical structure of the database. And there's some of the information. A lot of critical sequence numbers are also stored within the control file. You can't do anything if your control file is damaged. And we use the terminology, you mount the database. When you mount a database, it means locate the control files, read them, validate they're okay. There's no good or bad. And recommendation 3 copies, that's what Oracle recommends, but there's no good or bad, there's no right or wrong, there's just conforming to your corporate standards. If your company corporate standard is there should be 3 copies of the control file on different disks, and all 3 of them get destroyed, you're in a lot of trouble. But that doesn't matter, because you say, our standards were 3 copies, I had 3 copies.
John, I have a quick question.
Please.
If for some reason I accidentally delete all my control files.
You can survive.
Well, I mean, if I know what the structure is and where everything is located, can that be recreated?
Yes, it can be. If you lose all copies of the control file, you are in a horrible situation, but there are ways out of it. You can, if you know the physical structures, you can recreate the control file. And as long as there was no other damage to either the control file, as long as there was no damage to the online logs, you can recreate a control file and your database will survive. So there are techniques for doing that. It's pretty straightforward, and since you've asked, I'll demonstrate it now. We'll save us time later on. A command, alter database, backup control file to trace, don't bother memorizing this syntax, though you might want to memorize my spelling mistakes, as /home/oracle/controlfile.trace. Then correct my mistake, change ZS for this. And what this will do is you'll see VI. If any of you aren't familiar with VI, we may have trouble with 1 or 2 exercises, but don't worry, they should teach VI in kindergarten, they really should. But if we look at that file that I just generated, we'll see exactly what you're talking about, Scott. That command there didn't back up anything. What it did was generate this command, which I should see down here. So it generated create control file. And what is in the create control file command? Never mind about that. Where are my online log files? Where are my data files? So we are creating at this point a control file which is empty except for the physical structures. So this is the bare minimum of information you need in a control file. Certain physical limits, the physical structures, the character set used to encode data within the database. And this is the minimal information you must have in a control file. There's actually quite a lot more in a control file. I mentioned already, if your online logs were damaged, you will not be able to recover through this technique because Oracle won't know, for instance, which online log file to use next. That information is not included in this command. You will have to interrogate the online log files themselves. Please?
The control file doesn't contain the sequence number, the last sequence number.
It does, in fact. It does. But because this command doesn't specify the sequence number, if you start up a database using a manually created control file, Oracle will have to go to the online logs and ask them, what was your last sequence number? Because some information does exist in two places.
Is that what the reuse command does?
No, reuse just means don't throw an error. Where was reuse? Is it up here somewhere?
Well, it's right there in the crate, control file reuse.
That just means don't throw an error if the file already exists.
Oh, okay.
Yeah. So what this means, because this information is so incomplete, Oracle will then have to go to these files and look at them and see what their log switch sequence number is. And provided it can get that information, it will then be able to bootstrap itself forward. But that is going beyond what I want to talk about now. But bear in mind, this is a nice example to introduce this point. This is the minimal information needed. But there is, in fact, quite a lot more needed if you're actually going to mount and open a database. So mount means open the control file. Open, the next stage, let me go through it now. What I'm going to do is kill my database with the command shutdown abort. Shutdown abort is a spelling mistake. You can abbreviate it to SHU. This is functionally equivalent to pulling the power out the back of the server. It just cuts the ground out from beneath Oracle. And startup is actually staged. I'm getting ahead of ourselves again, but startup no mount. This builds the database instance. It builds the database instance. What does that mean? Memory structures, processes. Alter database mount reads the control file, all copies of it, and validates they're okay. So for that to succeed, the control file must exist and not be damaged. Alter database open uses the contents of the control file to locate the online logs and the data files. Okay. Temp files. These are, as the name implies, used for temporary objects. Temporary objects, large sorting, sort space, global temporary tables, data used for hash merges. It's temporary structures used by sessions. More of that later on. Strictly speaking, you can operate a database without temp files, but any production database is going to need temp files, and indeed temporary table spaces, because just as table spaces consist of data files, we have temporary table spaces that consist of temporary files. So, select star from $v table space, shows me these table spaces, including one called temp. But we don't know what type of table space it is now. If I select table space name from DBA table spaces, right, we see temp, so we get that information echoed out, but then it gets a bit more interesting. If I select name, just call name format A 60, select name, and from $v data file, I get 7 rows back, none of which seem to have anything to do with temp. And that's because we need to go to another view. We have $v temp file. And that shows me the temporary file. If I select star, we'll select ts hash name from $v temp file, we find that table space 3 is made up of that file, and table space 3 is indeed the temporary table space. So $v table space shows you all your table spaces. DBA table spaces shows you all your table spaces. But then we have separate views. We've got $v data file and $v temp file, and we also have DBA data files. And guess what? We have DBA temp files in which there will just be one entry. So bear in mind, for physical structures, don't forget that one. Right. The number of views we're throwing at you is terrifying, isn't it? I'm sure you memorized them all already now. So temporary files, in temporary table spaces consist of temporary files, and temporary table spaces are used for temporary segments, and temporary segments are used for temporary data, such as sort space, interim result sets. Temporary tables, indexes on temporary tables. Now, and that's where we move on to our next query. If you look at the dollar table space, Oracle really doesn't know what's in this. Describe, not select, mixing up queries. If we just put that, Oracle really doesn't know what's in these table spaces. It knows the name, whether they should be backed up, but that's about it. Whereas if we look at DBA table spaces, we get a lot more information. In particular, we get what's called the contents. So it selects table space name, contents from DBA table spaces. And there we see, that table space contains temporary data, these table spaces contain permanent data. And for example, if I try to create a permanent table, perm C1 date, if I try to nominate table space temp, can't do it. Yeah, so you have very little control over temporary objects. Oracle creates them as necessary.
John, what protection is necessary for temp files in terms of backup?
Theoretically, no protection at all. If you are backing up your database manually, you can back up temporary table spaces. If you back up your databases, as we are going to advise you to do with the RMAN utility, in fact they will never be backed up. And the reason is that they do not contain permanent data. No redo is generated for them. So even if you restored a temporary table space from last week, there will be nothing in the redo log with which to roll it forward. So Oracle takes the approach that since you can't recover them, there's no point in backing them up. And it's a matter of speed. Look at this. If I create table space, TS2, data file size, if I create that with a 100 megabyte data file, we'll see how long this actually takes. Oops, I need to give the data file there. Data file, create table space, not create table. What I'm going to do is set the timing on. This is a SQL Plus facility that will time things. So if I create table space, TS2, data file size, 100 megabytes, it's taking a while. And that's because Oracle is formatting that 100 megabyte file into 8 kilobyte blocks, 4 seconds. Alternative syntax, I'll create a temporary table space. Temp2, temp file size, and I'll make that a gigabyte. Then I'll correct the spelling and do it again. And wham, straight back. That thing is not formatted. That 1 gigabyte of space has not been formatted in any way at all. And that's why recovery of temp files is simply not an issue. If any temporary file gets damaged, you just drop it and create it instantaneously. I'm going to drop that thing. Well, I'll leave it be for now. Right.
To the students here, I'd like...
Let's see, we're nearly at the end of the chapter, aren't we? Please.
Yeah, just out to the students. Wondering if you have ever had a situation where yourself as a programmer, developer, or staff that is developing applications have said, I'm creating a temporary table in order to hold some data for the life of my session. And have you dug in and found whether they're using an actual Oracle Global Temporary Table, or some people say, well, I'm using a temporary table, and they try to create it at the beginning of their session and drop it at the end, so it's really not a temporary table. And I would, caution against that, running DDL during a live application, or even using a static heap table when what they really need is a global temporary table. So actually, just feedback to me in the chat thing. Have you worked with global temporary tables before, GTTs? Kathy's going to know. Yeah, it's good to be aware of. Scott's using temporary tables. Real tables, Scott, or temporary tables, or global temporary tables?
I'm not sure I know what the difference is.
Yeah. Okay.
In fact, if anything, I at some point like to talk to somebody about temp tables, because I'm divided as to whether I should create one big fat temp table or multiple temp tables, clean them out periodically. I don't know.
Tell you what, in the chapter on managing tables and table types later in the book, we'll dig in on the distinction between the two. But I wanted to raise the question now because it has to do with temp space. And you just saw John create a 100 megabyte data file, took 4 seconds or almost 5 seconds, and yet created a temp space, a gigabyte, and it came back in a flash, sub-second. And the same kind of response time can be, improvements can be achieved, and overall scalability things can be achieved when using global temporary tables when they're proper, when somebody really needs a temporary structure. So glad I asked the question, and we'll put it up on the to-do for when we get into managing tables and other table types.
Yeah, it's an important
back to you, John.
It's an important capability is the global temporary table. If I remember correctly, it came in with 8i. We forgot at our introductions to ask you what releases you're on, but I'm going to assume you're all on 11 of some sort or another, but we can check back on that later on. But these things came in with 8i, and they're very powerful performance enhancement. Okay, now, parameter files. The parameter file is used for building the instance in memory. Startup parameters for database and networking options. How we build the instance. The networking parameter files, we won't be talking about them for a while. We're going to be talking about the instance parameter file now. So the instance parameter file. When you build your instance in memory, so coming back as ever to my diagram here, when you build this thing in memory and start the background processes, you have a certain amount of control over how big the memory structures are. A certain amount of control, but rather less, over the background processes. But clearly, you need to know how big the memory structures are, because that's a vital matter, the tuning and the physical capacity of the node on which your Oracle server is running. Now, how many parameters are there? Well, if we look at the view $v parameter, which we saw, $v parameter, well, how many parameters are there? Well, easy enough. Select count star, or count 8 from $v parameter. And we find that there are 347 parameters, publicly available parameters, in this release of the database. What release is it, by the way? Another query you're going to get used to running on every database you ever log on to. Select star from $v version. And this is 11203. Yeah, 11203 Enterprise Edition, happens to be running on Linux. And depending on your exact release and your exact platform, you will find you get a different result coming back. So there are 347 parameters. However, you don't have to set them all. Oracle very kindly, from release 10 point something, even gives you the extra column. Is it a basic parameter? And parameters are considered to be basic or not. Basic or not. Let me just check exactly what the values are for is basic. What we'll actually do is select is basic, count star, count 8, $v parameter, group by is basic. And we find that Oracle considers 30 parameters to be basic. The general idea is that the basic parameters probably need to be set for every database. The non-basic parameters, well, depends what you're trying to achieve. But you almost certainly want to set the 30 basic parameters. So what are the 30 basic parameters? Well, call name, format A30, call value, format A30. Oops, forgot to return, there we go. Right. So these are the 30 parameters that Oracle thinks probably every database should be setting. Cluster database. Right. This is Oracle saying you should be using rack everywhere. This is single instance, therefore false. Compatible. As you upgrade your database, you change this parameter. We are running compatibility mode of 11.2, whereas in fact we are 11.203. So we've installed a later version of the executables than are actually enabled within the database. There are some reasons why you might want to put that back to an earlier release, which is done by default. It defaults to the base release, 11.2. So all the features of 11.203 are not in fact available to me at the moment because of that. Where are your control files? I was wondering why none of you asked me this. When I issued that command, alter database mount, way back somewhere here, when I said alter database mount, well, no mount built the instance in memory. It read the parameter file to build the instance. That located and read the control file. How did it know where the control file was? Because this instance parameter tells it where the control file is. So the instance knows that there's one copy of the control file there, another copy of the control file there. Okay then, well, let me... Good, thanks Dave. To summarize then what we've covered in this chapter so far, we've covered so far, thanks Paul for that, 3 physical structures. Remember, your data files are the physical structures that make up the table spaces. The table spaces store the logical structures, such as tables. Then we looked at the redo log, and the redo log is a logical structure consisting of 2 or more groups, and the groups each consist of 1 or more physical members. And the physical members, those are the structures that store the change vectors applied to the database and eventually to the data files. Then we looked at the control file, a small physical structure that contains more than anything else, more important than anything else, it contains pointers to the rest of the database. There is quite a lot more in there than those pointers to the rest of the database. There are lots of critical sequences stored in there as well, but it's the physical pointers that are really necessary to proceed from the mount stage to open. And speaking of that, to start up a database instance in what we call the no mount mode, the only physical structure required is the parameter file that we've just started looking at. Then to transition the database instance from no mount mode to mount mode, we need the control file. To transition the database from mount mode to open mode, that's when we need to be able to access all of the data files and the online log files. So parameter file. As we were saying, there are... I've lost my session. What you won't know is that while I was out of the office, our new kitten jumped on my keyboard and, among other things, managed to close my putty sessions. Let me get them up again. I'll change the font on that. Now, SU minus Oracle and SQL plus / sysdba. Right, the parameter files. There were 30 basic parameters. I'm not going to go through all 30 of them right now by any means, but we just pick up a couple of the more critical ones that are required at the stage of opening the starting the database instance in no mount mode. So read our parameter. And I shall one minor point, this business of true and false. Remember that within SQL there's no such thing as a Boolean data type, hence we always have to put that into string. That changes with release 12c. Of course, oracles have Boolean data types in PL SQL, well, since the beginning. So these are the basic parameters. I'm not going to go through them all. Cluster database, yeah, compatible. That's the critical one. Where is your control file? Block size, remember, how are we going to format the buffers in the buffer cache? Because the buffers in the buffer cache must, of course, match the size of the blocks in the data files. You couldn't cache a 16 kilobyte block in an 8 kilobyte buffer. So block size, 8 kilobytes is the default. There are a few others, but we'll be going through all of these later on. Possibly one worth mentioning at this point. Now that will do. That will do for now. So the parameter file, name the database. So that's a required one. I should mention there is one required parameter. From 10G release 1 onwards, there's one required parameter, which is dbName. So what this means is that when we start up the instance in no mount, the instance will know that it's meant to be opening a database called class, and a few other structures as well. Then when we transition to mount mode, it will read that parameter, I've truncated that unfortunately, to read the and locate the control files. And at that point, of course, it will look at the header of the control file and see, are you actually a database called class or not? And it will fail to mount if that does not match the name of the database stored in the control file. So that's a parameter, a memory structure, which must match the physical structure, the control file itself. Now, but they're 370 odd parameters. Here we have some of the critical ones: name the database, block size. That's one of the memory structures. Our database buffer cache will be 25 megabytes big, and there we've got 3 copies of the control file. Now there are 2 forms of the parameter file. The P file, the SP file. Some people will call the P file the init file. What else is it called? Init file, a P file, a parameter file. The SP file is also known as the server parameter file. It's a binary file. You can use either. All databases should be using an SP file, but there are occasions when you will want to revert to the much older P file that dates back to the beginning of Oracle. The SP file was introduced with 9i release 1. All databases should use it. There is also a password file. This is an optional structure. An optional structure. Most databases, I'll backtrack on saying most databases. Some sites have rules that there must be no password files, which is to do with security. A password file, it's to do with security and how you authenticate to the database. We'll talk about that much later on when we talk about creating users. For now, the password file is not used by any regular user. It's not used by any regular user at all. If I connect a Scott password tiger, that password is being authenticated, it's a hashing algorithm, is being authenticated against data stored within the data dictionary. It is not being validated against the contents of the password file. It is not being validated against that. The password file is used only for sysdba connections, such as well, connect sys/oracle as sysdba. That syntax instructs Oracle to go to the password file. The reason for this is that you can't validate a password against the data dictionary if the database is not open, because the data dictionary is tables. So if the database isn't open for any reason, you wouldn't be able to get to the password stored within the data dictionary. So for these privileged connections that are used for startup and shutdown, we can authenticate against an external file called the password file. VDOLA PW file users will show you the names embedded within it. If I select star from VDOLA PW file users, we see sys is the only person whose password exists in that file. So for use for connecting before the database is open.